All right. We're going to do a few things today. We're going to talk a little about depth-first traversal for PA3. We're going to talk about the ODP that was posted this morning. We'll do a quick run-through on PA3 code just for kind of having another example of stacks and queues. And then we're going to play with tries. And I made you a bunch of try nodes. So we're going to pass these out, and you're going to work in groups at your desk, and we'll play around with manipulating a try by inserting things into it. And the ODP is related to try, so we'll do a bit of coding through the ODPs, and we'll do some hands-on with these worksheets. So let me start with depth-first traversal. And this is an algorithm where pseudocode doesn't necessarily help you. So there's two ways to do depth-first traversal. You can do it with a while loop, and you're going to have to implement a stack and use the stack, and in that case pseudocode is going to be a big piece of that. But in practice, we usually do all these things recursively. And the recursive algorithm really comes from the definition. So we're talking about left node right traversal. And the algorithm for left node right traversal is recursive. Okay. Let me look at it after class, if you can save it without getting booted off the server. So left node right traversal is recursive, right? And the way we do LNR traversal is do LNR on the left tree, and then print the root data, and then do LNR on the right tree. Okay, that's sort of the definition of LNR traversal. First traverse the left subtree, then print the root, then traverse the right subtree. So it's inherently recursive. And like I say, pseudocode doesn't really help you with this. Really, you kind of have to just sort of write the code. And so if we write code to do an LNR traversal on root, right? Do LNR on root left, print root data, and do LNR on root right. And that's almost your whole function, right? With one extra line of code, which is we need a base case. We need a way for this recursion to end. And with traversal, the easiest way to end is just if root equals null, return. So that's your depth-first traversal. Were you asking about traversal or search?
I would like to see about breadth first.
Oh, breadth first. Oh, I thought you said depth first. Okay. All right. Well, that's breadth first, depth first. So breadth first is the one algorithm that's not recursive. Okay, sorry, I should have looked at your code then. But let's do some pseudocode. So insert the root at the tail of the queue, right? The queue starts empty. So insert the root at the tail of the queue. And then while the queue is not empty, do the following. remove the head of the queue. I'm just going to call that temp. Print temp data. If temp left is not null, insert it into the queue. And if temp right is not null, insert that into the queue. Queue starts empty. So as long as the queue is not empty, remove the head of the queue, print out its data, and then insert its left and right subtrees back into the queue if they're not empty. And that's your whole breadth first search traversal. So start off by putting the root in the queue and then just keep removing, printing, and pushing in the left and right subtrees. And eventually you'll run out of stuff in your queue and then you're done. You've printed every node. Does that help with your pseudocode?
I think so.
Okay, catch me after class if not. All right, so let's look at the ODP. So we got ODP 240, and we're playing with tries. And I'm probably going to have 2 or 3 ODPs related to tries. And they're all going to use the same trinode structure, which looks like this. And remember, when we think about tries, we think of our nodes as looking like this, right? 26 letters and then an end of string flag. We're not going to worry about the end of string flag for this ODP. But these 26 boxes labeled A through Z, these are each pointers to other nodes, or they're null. Okay, so we could store 26 pointers called A, B, C, D, X, Y, Z, but that's hard to work with. So instead of storing 26 individual pointers, we have an array of pointers with 26 elements. So we can think of our structure as looking like this. I'll switch over in a second. All right, we got an array of 26 pointers to struct trinodes, and we've got an end of string. We could think of our structure as being like this. There's a struct trinode called letters bracket 0. There's a struct trinode, these are pointers, called letters bracket 1, all the way down to letters bracket 25. So there's your 26 pointers corresponding to the pointers coming off of each of these boxes. So this first pointer, letters bracket 0, corresponds to the letter A. The next one is B. The last one is the letter Z. And your function, which is find try letter, is given 2 arguments. It's giving the root of your try, and it's given a single character C. So the root of the trie is a struct trinode star. All right, that's supplied to your function. And you're also given a single character, which I'm just calling C. And the goal of this function is to see whether or not that pointer in the root points to anything. So if that pointer is pointing to null, your function should return a 0. If that pointer points to something not null, your function should return a 1. So if you have a trie set up like this and the letter A points to some other node, if I call your check trinode function and I pass it the root and the letter A, it should return a 1. If I pass it the root and the letter M, it should return a 0 because M is pointing to null. In fact, everything is going to return a 0 except if I pass the letter A or the letter C, if this is what your node is set up like. If your node was set up like this, right, if that was what root was pointing to, then if I pass it the letter T, it should return a 1. Anything else should return a 0. So your goal in your function is simply to take the root and find the corresponding pointer that goes along with whatever letter you're passed and just see if it's null or not null. And so the corresponding letter is basically root, arrow, letters, bracket, some index I. So if this thing equals null, return 0. Otherwise, return 1. So the whole trick is, what is the value of this index that you want to check? Well, you can hardwire this pretty easily. Yeah. You can use awk and do it pretty painlessly. So you could make 26 if statements. Logically, this is what you want, though. If you're looking for the letter A, you want your index to be 0 so that you check root, arrow, letters, bracket, 0. If your letter is H, you want to check root, arrow, letters, bracket, 7, because it's that node index 7 that corresponds to the letter H. So does this make sense to everybody as far as functionally what you want to have happen? Right? Find the index that corresponds to the letter and then check whether that pointer in the letters array is null or not null. So I made a note in there that you can assume we're using Ascii coding, right? Which means that A is always going to give you a 0, B should always give you a 1, Z should give you a 25. So how can we find this index from this letter without doing 26 if statements?
Subtract 65.
Subtract 65, right? Or subtract the character A, which is 65. And that's legal syntax. So if I take the C, which is a character, right, the ASCII code of a character, and I subtract single quote A, which is the ASCII code of an A, this will give me 0 if C was A, 1 if C was B, 25 if C was Z. So you do this calculation, right, for I, and then you check that element in your letters array. So if all that makes sense, it's like 1 or 2 lines of code, right? And this is a useful trick to be able to do anyway. If you didn't want to do that trick, if you don't want to trust ASCII codes, if you're living in this parallel universe that never invented ASCII codes, right, here's another thing you can do. You can make a string of your 26 letters, and now take your character C and try to see which one of these letters it's equal to. And the index of the letter that it matches, that's this index up here. So that's a more general way to do this. But for this, you can just subtract the letter A, or 65. So that's all you need for this ODP. Does that make sense? Okay. And where we're going with this is probably the next ODP or the one after. If we take a node and we take a letter C, we can go to that and we can say, is that null or not? Suppose we're looking for the word cat in our try. We take the first letter of cat, that's a C, see if that pointer is null or not. If it's null, you're done, cat's not in the try. If it's not null, see what that points to, and now look for the second letter, A. If that's null, you're done, cat's not in your try. If A is not null, see what that points to, look for the third letter, which is T. If it's not null, see what that points to. There is no fourth letter, so now check to see if that end of string bit is set. And if it is, cat is in your try. So we'll build up to that in a couple of ODPs. But for now, we're just playing around with the node structure itself and taking a letter and using it to figure out what the pointer is pointing to. All right, let me do a quick run through on my code for PA3. And I think everybody was pretty much on the same page with this, so we don't need to go into a lot of detail here. I did a few peculiar things. I had two structures instead of one for stacks, one for queues. The only reason I did that was because I wanted this thing I'm calling a tail pointer to speed up my queue processing. Weren't required to do that. If you're just using plain old linked list, you can use a single struct node, and when you want to get to the tail of the queue, you just start at the head and just move till you get to the end. But I coded this up with a tail pointer just to make it a little faster. So stack routines, right? Initialize, push, pop, see if the stack's empty, and display the contents of the stack. And then a similar set of 5 routines for queues. You can combine these. A lot of people combine them, and that works well. I'm lazy, so I wrote separate routines. Well, different kind of laziness. More typing, less thinking. So I wrote separate routines for stacks and for queues. And my exit is the routine that clears up all the memory. So it takes 2 sentinel nodes, and it frees all the nodes in those corresponding lists. So S node and Q node are the sentinels to the stack list and the queue list. Pair of defines, which we talked about for my magic values for my modes. So 0 is stack and 1 is queue. And then I don't have to have magic values. I can say set the state equal to stack. So I'm starting off in stack mode. Initialize my stack and my queue, so I create empty sentinel nodes, right? Nodes that point to null. My one-line welcome message. Ask the user for input, and then get the input. So here's the parsing section. So for me, I started off by parsing to see if you had an integer. Because if the person types an integer, I want to add that to a structure. So first thing I do is my scanf, see if it returns a 1. If it does, they type in an integer. So I'm going to do some kind of insert. Should I push or should I add? Check the mode. So if the current state is stack, then do a push, otherwise do an add into the queue. I blatantly ignore the possibility of overflow here, so that's a feature or bug. Otherwise, they did not type an integer. I'm going to assume they typed a command. So now I just switch on the first letter of their input. If it's a queue, call my myExit code to free the memory and just return from the main program. If it's an S, I want to be in stack mode, so set my state to stack, print out a message that we're in stack, display the current stack, and we're done. If it's a queue, same thing, set the state to queue, tell them we're in queue mode, display the queue, and we're done. If it's a P, we want to remove whatever's in the front of the structure, so again, check the state variable. If they're in stack mode, see if the stack's empty. If it is, print an error message. Otherwise, pop the stack and print out what you popped. And then exactly the same code for queue. If the queue is empty, print a message. Otherwise, remove the head of the queue, print it out. Anything else is an unknown command, so show them a help message and print out a prompt and go back to the top of the loop. And my loop also exits if fgets returns null, which happens when you hit Control D. So you can kick out of this by putting in Control D instead of typing in a command, or you can use the Q command. Generic help message, bunch of print statements, freeing the memory. So you did this in PA2, right? So just start at the sentinel and free it, but before you free it, make a note of what it's pointing to. So set s equal to the next node, free the sentinel, and then move to that next node. So exactly the same for the stack and the queue. And then queue routine, so this was the only thing that was slightly funky, was the add function, because you added the tail. So here's the setup. You've got your sentinel node. And I've got three pieces to my queue nodes. I've got data, I've got next, and I've got tail pointer. And I only use tail pointer in the sentinel node. I ignore it in all the other nodes. So here's a second node, and so on. And here's the end of my list. And I don't care about tail pointer in any of these. So there's some number. Okay, so I want to add to my queue. That means I have to insert at the end. I want to create a new node. So make a new node. It's got some number. I don't care about tail pointer. I want to stick it on the end of the list. Okay, if you don't have a tail pointer, you start here and you just move until you get to something that points to null, and you're done. If I have a tail pointer, my tail pointer is always pointing to the last node of the list. So when I want to insert a new node, I do the following. I follow the tail pointer, which gets me right to this node, and I change this to point to my new node. And then I change tail pointer to point to my new node. So it's a pair of operations regardless of how much stuff you have in the list. And as long as I update the tail pointer each time, I can do this again and again and again. When I have another new node, tail pointer will take me here, so I'll change this to point to my new node, and then update tail pointer to point to my new node. The one exception to this, though, is if your list is empty. So I have some arbitrary data in here. An empty list, my sentinel points to null. Where should my tail pointer point? I could make it null. I could point to the sentinel, but I can't point to the last node of the list because there is no last node in the list. So this is a bit of an edge case. So there's two things that happen inside the add function. I create a new node, I sent the data to the number I set next to null. So I check to see if the sentinel is pointing to null. If it is, then I go ahead and point the sentinel to the new node, and I set the tail pointer to the new node in the sentinel. Otherwise, see what node the tail pointer is pointing to, have that thing's next field be equal to the new node. So that's setting up this red line. And then change the queue's tail pointer to be temp. That's setting up the green line. So that's your insert, remove. You just read the first element and return it, and free it before you exit. The list should never be empty. Okay, so my understanding, which I should have put in comments in the top, is that you never call this on an empty queue. And in my main program, remember, I check to see if the queue is empty. If it is, I print a message. Otherwise, I go ahead and call the remove function. So if you happen to call this on an empty queue, I do something bizarre. I just return a negative 999, right? That's not a reliable way to tell if the queue is empty, because you might have a minus 999 in your queue. Okay, but this was kind of a halt and catch fire sort of thing. Should never happen that this is equal to null, because I'm not going to call remove unless the queue is not empty. Display is just a regular traversal. Queue empty just tells me if the sentinel is pointing to null. And then set of stack routines, almost exactly the same, except your push goes in the beginning instead of the end. And that's the whole list of functions. So different ways to implement this. And like I say, the code that I looked at looked really good, so no concerns there. All right, any questions on any of that? All right, let's play with some tries. So I have some pages of nodes here. So what I want you to do is put yourselves in groups of about 3 people each. We're not going to work on the boards. You're going to stay at your desks. So you can move around. You can move desks if you want. But find a group of about 3 people to work with and grab 1 sheet per group. And I'll tell you what we're going to do with these once you're in groups. All right, so this is a try, and it has a root, which we're just going to assume is this first entry, this first node on the page. The root is never going to change. You're never going to change the root to some other node. It's always going to be this node, okay, whatever we do. And we're not going to delete anything from the try. We're just going to keep adding words to the try, which is always rooted at this node right here. And we're going to assume that if there's no arrows coming off one of these blocks, that block is equal to null. In other words, it's pointing to null. And end of string, we're just going to assume is a 0 unless we write a 1 in there. Okay, so this minimizes erasing. So this root node right now is basically an empty try. All of the pointers are null. There's nothing stored in here. All we have is a root node. Okay, so let's insert 1 word into here, and I'll do this with you on the screen. Let's insert the word at, A-T. So how do we insert? Start at the root and find the pointer that corresponds to your first letter, which is A. Okay, if it's null, then we're going to have to create a new node and point to that new node. If it's not null, we're not going to create a new node. We're just going to follow that link down to whatever node it's pointing to. Okay, so A is null right now. It's not pointing anywhere. So we're going to create a new node. I'm just going to start with the second node here. And I'm going to have A point to this second node. Now, it's not pointing to the letter A. It's pointing to the node. It just happens A is on the left. But the A is coded in the fact that I'm got the pointer from position A coming down here to this node. Okay, second letter is T. Check node T in here. If that was pointing somewhere, we would simply follow it to a third node. If it's not pointing anywhere, if it's null, we'll create a new node and point to that. So T is going to point to this node, say. Go to the third letter. There is no third letter. We've reached the end of the string. And so in this node, we're going to set the end of string flag to be a 1. And bingo, we've just stored the word AT in this try. Okay, let's store the word AB. And I'll do this one with you too, and then you're on your own, but I'll walk around with you. So AB, first letter is A. Again, start at the root. There's the letter A. It's already pointing somewhere, so we don't create a new node. We just follow that down to this node. Second letter is B. Check the B pointer. That's not pointing anywhere, so we have to make a new node. So have this point to a new node. Let's just go right here. So now we're on this node. Third letter is end of string. So down here we mark the end of string bit and we're done. We've stored AB. And I'm just going to write down over here on the side what the actual word is, just for reference. That's not actually part of the structure. All right, you got the idea? So go ahead and insert ATT. And I'll come around and see what you're doing. Alright, you still have AT and AB in there?
Oh, people need to erase them.
No, don't erase them.
Alright, so then just make this one 1. 31. And then AB, we need to have A and then B. Just make a new one.
You got this?
This word.
Okay. Good, cool. Okay. All right, good. So let's go on. So let's go ahead and put in a cat.
Just write down the number.
No, the C would have to come first.
So you can use
So yeah, when it's all to begin with, we're going to have to point to a new node. Because if you point here, you're saying that C.
That means we did this wrong. A, B here, A, T here, and A.
Oh, okay,
Right.
yeah.
Okay, catch.
Some of it will. So I think I'm more
So if you do a C down to here, you're saying that C, T, is part of your trial, right? But now you added CT. You added C followed by T to your try also. CT is not part of your try, right? But since this C points here, and that T points here, and that's set, that means CT is in your structure also. So if this is null to begin with, you got to point to a new node.
So for every letter in your
Yeah, you got to point somewhere new, unless you wanted to begin with a C and an A. Right? I mean, a C and a T. You cat.
Perfect. Granted, I've never done
Good. Oh, good. You labeled your node. Okay, good. Awesome. That's awesome. All right, you got cat?
Yeah, C goes all the way down here for A.
Good, perfect. All right, did I already see yours? All right, so slightly trickier. Go ahead and add CA.
Maybe. Do C and then go down to oh yeah, and the your first letter dot last name.
So A has to point to another place?
No, you don't want to change anything that's already in there.
Oh, we
No,
know.
C
is right here, so this 8 points to here.
There you go.
Oh,
Cool.
There we go. Oh. That's just an extra. Where's the erasure? Oh, I don't know.
Sure.
I'm curious what it's so when we did cats ended before the T.
Yep. Yeah. There it is. Right. So C goes down to here.
I'm actually thinking it's that one. C goes to
T goes here. A goes down here. You set that to a 1. Now you got CA.
You're going to need every combination.
Makes sense.
Cool. He goes to
Alright, we're taking CA. Set the bit to a 1. Cool.
Alright, where's the CA? And the statement for.
Okay, just send that 001.
Yep.
A.
Cool, perfect.
Are you finished for this? Someone send me
The paper one? Or the chat one?
So you just change your string to 1 and add it to my graph.
At least I'll do it in the next few days.
I got it.
Alright, so I think you've got this, so let's just throw a few more in just for practice. So let's add an apple.
From here?
Oh, yeah, you're right.
And then from here.
This is like a first first try. Yes. So we already have.
Is it 2 P's for apple?
It is.
Not much you go over 10.
Not that it's not like I just don't care.
Where's your 8? All right, here. Okay.
No wonder it was this long. Yeah, well, perfect. I heard that before.
So A is only PP in here. A is only PP. And then only to
A was already pre-initialized from the earlier version. So if A is on, we simply all point through to that node. And then we check the next letter, P, is null or not.
Cool.
P was originally to the assigned page which is all the way down here.
So you actually, if you actually put these numbers in here, these are memory addresses.
I'm like focusing this right. It's literally.
Nice.
Wait, that's exactly the same.
All right, does this make sense to everybody? Because it looks like you're all doing this perfectly. And you'll probably see this on the final, so free points. So yeah, so somebody started drawing a picture back there on the board that looked kind of like this. Right, so your root basically has these 26 children, and each of these has 26 children. Right. Of course, it's a language tree, right? And so if you want to find a word, you start at the root. If you're looking for A, B, you come down the A and you come down the B, and if there's a node here, then you got A, B in there. And the end of string is basically telling you when even if you've got other stuff coming off of here, do you have a word that ends at that location right there? So using this structure is pretty straightforward, right? If this is what your try looks like, and you want to know, do I have a cat in here? Start at the root, look at C. If it's null, you're done. There's no cat. It's not null, so follow that, and now look for your second letter, A. It's not null, so follow that, look for your third letter, T. It's not null, follow that. You're at the end of your word, so check the end of string. That's a 1, you've got a cat. Do we have cats plural? There's your C, comes down to here. There's your A, comes down here. There's your T, comes down here. Check your S. S is null, there's no cats, plural. And so searching is just a matter of starting at the root and following the right link corresponding to each letter of your word. So you make a loop that goes through for I equals 0 to string length of your word, takes each letter, subtracts A from it in this case, uses that as an index into your pointer array, and follows the pointer until it's either null or you get to the end of your word and your end of string is a 1. And then your word's either not in there or it's in there. So very efficient to search, very efficient to insert. No matter how much stuff we get in this tree, inserting a particular word takes the same amount of time whether the try is completely empty to begin with or it's got a billion words in it, right? Other than maybe having to create some nodes that weren't there to begin with. But 10-letter word's going to take you 10 operations, right? As you've been doing, to insert apple, you had to do 5 things, maybe 6 things. So that's basically tries. And like I say, I'm not going to have you code a full-on try, but we'll play with them through some ODPs. So tomorrow's ODP, I will probably give you a word and ask you to search the try for it. So, and then maybe the last ODP, I'll have you actually insert a word. So we'll see how that goes. All right, I will let you out 40 seconds early. So see you next time. You can keep these or you can toss them. It's up to you. Something to do.